Hello and welcome to this lecture on Fourier Convolution. This lecture is a continuation from our discussion on the Heaviside step function, and it's a part of module 2 of your course in Mathematical Physics 3. This is the plan for this lecture. We shall actually go back to some of the functions that I had given to you as exercises in the previous lecture on the Heaviside step function, and we will try to find out the Fourier transform of some of these discontinuous functions. Like I had mentioned in the previous lecture that it's important that you do the exercises in the previous lecture, so because we'll be just taking our discussion forward from there. Then this will help us to obtain the Fourier transform of two important functions that we had discussed earlier. One was the Signum function, and using the Signum function we will obtain the Fourier transform of the Heaviside step function. After that we shall go to the concept of convolution. I'll introduce to you the notion of convolution of functions and what it really means to perform convolution between two functions. And then this will take us to a very useful theorem known as the Fourier Convolution theorem. And finally we will end with some of the properties of Fourier transforms. We will prove a couple of them using the Fourier Convolution theorem. So moving forward, this is a function, a very common function which is used in modeling of electronic circuits. This is known as a gate function. So what happens in a gate function is this: we represent this as g of t. There is a parameter called as capital T. Okay, so when the value of small t lies between minus t and plus t, the gate function takes the value 1. Otherwise, it takes the value 0 everywhere. Okay, so we can express this gate function as g of t equals 1 whenever modulus of t is less than capital T, and it is equal to 0 whenever modulus of t is greater than capital T, where capital T is a positive number. So this is how we can express a gate function. Now we would like to find out the Fourier transform of this gate function. Now, as I had mentioned in one of my earlier lectures, you can find out the Fourier transform of a function if and only if it is absolutely integrable. Okay, so in this case this function is absolutely integrable, so we can easily find out the Fourier transform of this gate function. So we will use the definition of the Fourier transform. So all I have to do is, if I want to find out the Fourier transform of g of t, I have to do 1 by under root 2 twice pi integration of this function from minus infinity to plus infinity, and taking e to the power minus I omega t as my kernel. So this is basically our integral transform, and when we perform this we should be able to get the Fourier transform of the gate function. Now what happens is, here we are trying to integrate from minus infinity to plus infinity, but you can see here the gate function, it is having the value 1 only between minus t and plus t. Outside this range of values from minus t and plus t, the gate function takes a value 0. So as a result of this, what happens is our integration limits, it gets truncated. Earlier it is supposed to be from minus infinity till plus infinity. Now it will get truncated and it will be confined to minus t till plus t, because this gate function is 0 everywhere else and it takes a value 1. So within this range from minus t to plus, gate function takes the value of 1. So that's why we have only e to the power minus I omega t dt. Now integration of this is very straightforward. Okay, so this is equal to e to the power minus I omega t divided by minus I omega, and you have to evaluate this at the limits minus t till plus t. And when we do this, of course there is this minus I in the denominator. I take that I to the numerator, then we'll have to bring in another minus sign, so that minus and this minus will get cancelled. We'll get I by omega root over twice pi, and substituting these limits. Okay, so this is what we will get. Okay, slight mistake here, it should be I omega small t, not capital T. I'll make the correction here when I upload these slides in Google Classroom. So it should be small t. You will get capital T only after substituting the limits here. So you put the upper limit and you put the lower limit, you get this, and we immediately recognize this. This is nothing but minus twice I sine omega t. And then this minus and this minus will get this minus is there, and then we have a I and I square, which will give us another minus. So overall this will be plus. So this gives us the Fourier transform of the gate function to be twice sine omega t divided by omega under root twice pi. So that's the Fourier transform of the gate function. Now next, what about the Fourier transform of a constant function? That is a function which is having the same value everywhere. Okay, if I have a function which has got the same value everywhere, that's a constant function. What is the Fourier transform? Now if you look at this function as it is, this you cannot directly find out the Fourier transform of this. Why we can't find out the Fourier transform directly? Because this function is not absolutely integrable. Because if you try to integrate the modulus of k from minus infinity to plus infinity, the result will obviously be infinity, because it does not die down, right, as you go to larger values. So this is not absolutely integrable. So we cannot directly find out the Fourier transform of this function by just using the formula of the Fourier transform. So here we will perform a trick, and that will help us to find out the Fourier transform of the constant function. What we will do is, we will employ this result, the gate function that we have, we will use this result. You see, if you look at this gate function, what happens is, we have this, the gate function has got a parameter capital T, right, and capital T is a positive number. Now if I make capital T very large, okay, let's say from T, let's say instead of T I take twice T, what will happen? Then this will be the twice T here, and this will be minus twice T here. That will be the value range over which this will take the positive value of 1, okay, positive 1 it will take. Then if I keep on increasing this T, then what will happen is, the range of values over which the gate function takes 1 will also go on increasing. So in the limit, as T goes towards infinity, the gate function will be having the value 1 everywhere. Okay, so in other words, the gate function will become a constant function, and the constant value is equal to obviously 1. So you can write down the constant function as a limit of the gate function, okay, where you take the limit as T tends to infinity, and that gate function, whatever limit you get, you multiply it with whatever. But of course here we did not have 1 here, we had k here, no issues. We just take the limit of the gate function as T tends towards infinity, and that whatever limit we get, we just multiply it with k. That will give us the constant function that we are looking for. So we can write down this constant function f of t as k times the limit of the gate function as T tends towards infinity. Okay, now this is really straightforward, because we already know the Fourier transform. All you have to do is find out the Fourier transform of this one, which will be equal to Fourier transform of this as you take, when you take the limit as T tends towards infinity. So Fourier transform of f of t is equal to, k is a constant, will come outside, so limit as T tends to infinity, Fourier transform of the gate function. So limit as T tends to infinity, Fourier transform of the gate function we have just calculated, it is 2 sin omega t divided by omega under root phi. Okay, we now multiply and divide this by root over twice pi, and when we do that, in the denominator we'll have root 2 pi, it will give us twice pi, and that root twice pi, that twice pi, the 2 will cancel out this 2, and this root over twice pi, it comes, I'll take it in front and then combine it with k, we get this, and rest whatever is there we put inside the limit. Now this we already know, this is nothing but, this is one of the representations of the Dirac delta function. If you recall this, we had done this in one of the previous lectures, one of the representations of the Dirac delta function. Let me pull up that slide here. The Fourier transform representation of the Dirac delta function, it should be somewhere here, yes, this one. Okay, you can see here, this is nothing but this. Of course the notations are different here, but this particular limit is nothing but the Dirac delta function. So this we recognize immediately to be the Dirac delta function, and we substitute this. So this gives us the Fourier transform of a constant is equal to root over twice pi, the constant, times the Dirac delta function, where the peak is at omega equal to 0, which actually makes sense, because omega, right, the peak of the Dirac delta function is at omega equal to 0, and omega equal to 0 means zero frequency. Zero frequency means it's a constant term, it's a DC term. So it actually, this result actually makes sense here. Okay, next, this function, obtain the Fourier transform of the function defined in this way. Okay, this function, for negative values of t it is 0, for positive values of t it takes the value e to the power minus lambda t. We had already derived this result earlier, not here, in the first lecture on this one, when we are trying to find out Fourier transform. we had done an exercise where we had founded the Fourier transform of the exponential decay function, right? If you go back to my lecture on the Fourier transforms, you'll find out that we had done an exercise on the Fourier transform of an exponential function, right? So this is actually the same result we will actually obtain here also. So now we have to find out the Fourier transform of this one. So how do we proceed? Okay, so we can express this function in terms of the Heaviside step function, and we can express it like this. And I had given you an exercise in the previous lecture here, right? So I think this was the exercise. Yeah, exercise 3. Okay, exercise 3, question number D. Okay, so this was, no, not this one. Yeah, this one, question number B, right? So this was the question. In this question, I had asked you to find to express this function in terms of the Heaviside step function. So we express this function in terms of the Heaviside step function as e to the power minus lambda t into h of t, because h of t for negative values of t it will be 0, for positive values of t it will be 1. So all you have to do is just multiply that with e to the power minus lambda t. So that will ensure that it remains, it takes the value as e to the power minus lambda t for positive values of t, and it takes the value 0 for negative values of t. So once we have this, then it's fairly straightforward. You just need to find out the Fourier transform of this. So Fourier transform of this function will be nothing but 1 by root over twice pi minus infinity plus infinity f of t e to the power minus I omega t dt. This is just the definition of the Fourier transform. And of course the limits of integration from minus infinity till plus infinity, it will become 0 to infinity, and the reason for that is because from minus infinity till 0 the function is going to, this function is going to take the value 0 anyway. So it's going to be valid. This integral is only going to be valid. It's only going to be evaluated from 0 to infinity, and from 0 to infinity it takes the value e to the power minus lambda t. And when you, this is really straightforward to evaluate. It will just give us 1 by root over twice by lambda plus I omega. Okay, so we can write it like this: Fourier transform of this function f of t, and this function f of t can be written as e to the power minus lambda t h of t. So Fourier transform of the product of these two functions is equal to 1 by root over twice by lambda plus I omega. So this is the result that we obtain. Writing the result like this because this result will be helpful to us in solving another problem, okay, which is there in the exercises. So that's how we solve problems like this. Okay, this is an exercise that I have left for you. You can try it out on your own. So just like how we had e to the power minus lambda t on the positive side, in this case you have e to the power lambda t on the negative side for negative values of t, and for positive values of t it takes the value 0. So in this case also, using this representation of this function in terms of the Heaviside step function, if you have done the exercise in the previous lesson, you know what the representation of this function is in terms of the Heaviside step function, and you can show that the Fourier transform of this one is going to be actually this value. It's fairly straightforward. Okay, just follow the same steps as this example that I have shown here. Then the next problem is, I have a function which is given like this: for negative values of t, okay, for negative values of t it is e to the power lambda t, for positive values of e to the power minus lambda t, and for t equal to 0 it takes the value 1. Okay, so this is actually a piecewise continuous function, it's not a discontinuous function. So we need to find out what is the Fourier transform of this entire function. Now this is very straightforward. You don't have to actually do it using the representation using Heaviside step function. All you need to do is just use the results in the previous one. So this example, whatever result we had got, and this example, whatever result you have got, because if you see carefully, this function, it is basically a combination of the previous two functions, right? If I take on the positive side, if I take this function, that is this f of t, and I to that function if I add this part, okay, then that will give us this particular function. Okay, and we already have the Fourier transformations of, when you solve this, the Fourier transformation of this one and the Fourier transformation of this side, which is basically this. So it's just a matter of using these two results to show that the Fourier transform of this entire function will turn out to be equal to this. Then next again, this is again a discontinuous function. For negative values, it takes this function takes the value minus e to the power lambda t. For positive values, it takes the value 0. Following the same procedure as the example that I have shown, that is by expressing this function in terms of the Heaviside step function, you can show that its Fourier transform is basically this. That's your third problem. And the last problem is basically this. You have to show that you have to find out the Fourier transform of this function, which is given by this expression. Now this again is very straightforward. You have to use this result, because you can see here, okay, this negative values of t is identical to this function, and for positive values of t you have to use the example that we had done, right? This example, for positive values of t you have to use this part. So these two results you can just use, combine them together, that will give us the Fourier transform of this composite function, and you have to show that it is equal to this value. Okay, let's try out these exercises. They are really interesting problems. You can have fun actually doing these problems. Okay, so now let's move on. Okay, we are now going to use this result. Okay, this result that we have, even though I have left to you as an exercise to do at home, but we will be actually using this result in the next problem. The next problem is, if you recall, in the previous lecture I had introduced to you the Signum function. The Signum function, it takes value +1 for positive values of t, and it takes the value -1 for negative values of t, and at t equal to 0 it takes the value 0. So this was the Signum function. We need to find out the Fourier transform of the Signum function. Now how do you find out the Fourier transform of the Signum function? Again, it's very easy if we just use this result, because you see, can you see the similarity between the Signum function and this function? Okay, if you use your imagination a little bit, you will find, you see, what is the let's think about what is the effect of this lambda on this function. Okay, what if I make this lambda larger, or if I make lambda smaller, what effect does it have on this function? If you can actually work this out. If you make lambda to be larger, then what will happen is this exponential decay is going to be much faster, right? Because after all, this is nothing but your exponential decay function. So if the lambda value is large, then it decays much faster. So that means this graph is going to fall off to 0 much faster. Similarly, this will also fall off to 0 much faster. So increasing the lambda, what it will do is it will take both of these graphs, it will take it closer to the horizontal axis. So if you decrease lambda, what will happen? Then this graph is going to exponentially decrease much slower. So that means this graph is going to become more and more horizontal. Okay, as you decrease lambda, this graph is going to become more and more closer to the horizontal. So we could think of the Signum function as a limit of this function. Okay, the Signum function we could think of as a limit of this function. This function, take the limit of this function as lambda tends to 0. Okay, when I make lambda smaller and smaller, it becomes more and more like a horizontal line. That means it will become like a Signum function. So this function, when I take the limit as lambda tends to 0, okay, when I take the limit of this function as lambda tends to 0, then this function that we had solved in the previous in the last exercise, which we will be solving, it will tend towards the Signum function. Okay, and this Signum function, this particular function, okay, this particular function, it can be written in terms of the Heaviside step function like this combination of the Heaviside step function. So basically the Signum function is simply this combination of functions taking the limit as lambda tends to 0. Okay, this combination of functions will give us this and this. Okay, so if you have done the exercise in the previous lesson, you will actually know that this is the representation of this particular function. Okay, so when I take the limit of this function as lambda tends to 0, you will ultimately reach the Signum function. So then it's fairly straightforward. All you have to do is you have to find out the Fourier transform of this. That means you have to take the Fourier transform of this entire function as you take as lambda tends to 0, and the Fourier transform of this entire function, when you do this exercise, when you do the Fourier transform of this entire function will be actually this value. So we just take this result and we'll just insert this over here. Okay, so Fourier transform of this will simply be this result. Okay, and here we can very easily we can set lambda to 0. When you put lambda to 0 in this denominator, this will become 0. There is already that omega square, so we don't have to worry about the denominator becoming 0. So we can safely put lambda to be equal to 0, and the moment we do that, okay, this omega, and there will be omega square here, so this omega will get 1 omega will get cancelled, so that will give us the Fourier transform of the Signum function as 2 divided by I omega root over twice pi. Okay, so this is the Fourier transform of the Signum function. So we have obtained this using some other function. So this is fairly common, okay, in Fourier transforms. Okay, we use existing results, and it's not just Fourier transforms. In integral transforms, we use existing results to obtain other results in a much more simple way. Okay, so this gives us the Fourier transform of the Signum function. Okay, so next what we'll do is we'll now obtain the Fourier transform of the Heaviside step function. Okay, Heaviside step function like this. If you think of taking a similar approach like this, okay, if you think of taking a similar approach, then we could think of the Heaviside step function as, maybe if we have an exponential decay here, and that exponential decay, if we make lambda, take the limit as lambda tends to 0, it will become the Heaviside step function. That's one way to do it, right? That is, I think it was the first problem. Yeah, in this problem, this is the exponential decay. So here, if I take lambda as lambda tends to 0, we'll get a Heaviside step function. But then that method will be quite tedious, because we are, of course, we are writing this function itself as a Heaviside step function, but it is much more tedious to obtain this. We can obtain this, but it will be much more tedious. It's much easier to obtain the Fourier transform of the Heaviside step function using the Signum function itself. Okay, we can find out the Fourier transform of the Heaviside step function using the Signum function itself, because of this reason. Let's I had given an exercise in the previous lesson. Okay, so I had asked you, one of the things that I had asked you was express the Heaviside step function in terms of the Signum function, right? So we can find out the Heaviside step function in terms of the Signum function. Okay, and then it's just a matter of taking the Fourier transform on both sides. That will give us directly the Fourier transform of the Heaviside step function. So we can write down the Heaviside step function in terms of the Signum function by this. Okay, same thing. If you have done this exercise, you will know how this result comes in to the picture. So taking the Fourier transform of the Heaviside step function means taking the transform of half, and half times taking the Fourier transform of the Signum function. Now what is half? Half is a constant, and we have already obtained the result, Fourier transform of a constant. Okay, so Fourier transform of the constant is root over twice pi times whatever is the constant times the Dirac delta function, right? So the constant is half, so root over twice pi times half times the Dirac delta function, omega, where in terms of the omega, the Dirac delta function in the omega space, where the peak of the Dirac delta function is at 0 frequency, and half times the Fourier transform of the Signum function. This again we have obtained, Fourier transform of the Signum function is 2 by I omega root over twice pi. Okay, so we can just simplify this, and then we can obtain the Fourier transform of the Heaviside step function in this way. So this is the Fourier transform of the Heaviside step function. In just 2 steps we have been able to obtain, provided we know the Fourier transform of the Signum function. Okay, so with this we come to the end of these applications of the Fourier transforms on discontinuous functions. Next, I will introduce to you the notion of convolution of functions. Okay, because that will enable us to introduce the Fourier convolution theorem, which is an extremely useful theorem. So basically, convolution is a mathematical operation. It is an operation on functions. Okay, so when I take a convolution of 2 functions, what we are basically doing is we are expressing how the shape of one function influences the shape of the other function. Now this has got tremendous applications in instrumentation. Okay, so for instance, let's say I have a signal that I want to sample, and I'm sampling this signal using a instrument. This instrument will have a certain response, because it is not going to give me the exact value of the signal. It will have a certain response. So the convolution will basically tell us, okay, how this instrument, what kind of effect is the instrument having on my measurement. So for instance, an example of that could be, let's say I have a star, okay, a star which is very far away, and I'm trying to find out the spectrum of that star. Okay, so that means I'm trying to find out how much of energy is contained in the different frequencies. So let us say, just as an example, I have a star which is like not just a star, it could be a monochromatic source. So I have a monochromatic source, okay, which emits light at one particular frequency. Okay, so this is the light that is coming from the monochromatic source. and I'm using instrument, okay, that instrument does not just measure this frequency, it measures light at many different frequencies, and its peak is somewhere over here. Okay, I'm trying to measure the frequency omega naught is here, but the instrument that I'm using to measure this, it measures the signal, it measures that frequency, but the sensitivity of the instrument is much more at a different frequency. So this is basically how an instrumental response looks like. Okay, the human eye, okay, you could think of it as a detector. Okay, the human eye is basically a light detector. Human eye has got some sensitivity. We are not able to obtain. Our eyes are not sensitive to infrared light or ultraviolet light. It is only sensitive to a certain narrow range of frequencies. Okay, which is the visible range. So it is most sensitive in the yellow, right? So it could be like this source. It is emitting light in the let's say. Violet region. Okay, it's emitting light in the violet region. Okay, and it has got maximum sensitivity in the yellow region, right? So the fact that the instrument does not have maximum sensitivity where I'm trying to measure, that is going to affect the result. Okay, so the result that I'll be getting out of this instrument will not be a sharp peak like this. The result will be a smeared signal like this. Okay, that is because the signal that I'm trying to measure and the instrument that I'm using to measure signal, they are influencing each other. Okay, the shape of one is influencing the shape of the other. Okay, so this is known as a convolution. So the convolution of the signal and the response will give me a result which is something like this. Okay, so here the signal it tends to be narrow, and the response it tends to be wide, and it is more towards skewed. It is having some the response is maximum towards the higher frequency side. So both of these factors will come into the picture, and as a result we will have neither a narrow output nor a wide output. Okay, and of course the fact that the response is towards the higher frequencies, that means the signal is also skewed towards the higher frequencies. So basically these two signals, these two functions, okay, if you look at as two different functions, they are basically influencing each other's shape, and this is a result that we get. So this is what we call as the convolution of these two functions. So this is basically what convolution is. So it's got tremendous practical applications almost everywhere. Okay, it's got practical applications. Okay, so how do we define the convolution of two functions? So we just simply define the convolution as the integral of the product of one function with the other function reversed and shifted. So let's say I have two functions, f of t and g of t. Then the convolution is, it gives me one more function which we call as h of t, and it is expressed as h equal to f star g. Star means convolution. Okay, so f and g, you put a star in between, that means I'm convolving these two functions, and this will also be a function. This result will also be a function of the same variable t, and it is defined in this way. The convolution is defined as, okay, one function. Okay, you take it, you use a dummy variable tau. Okay, then the other function, what you do is you first reverse it. Okay, this you putting minus sign. Okay, just refer to one of the lectures on the Heaviside step function. You put the variable here is tau, you put a minus sign in front of the variable, that means you are reversing the function, and then you put another quantity over here which is t, that means you are shifting it. So you are doing this function g, I am reversing as well as shifting it, and then I take the product of these two functions, and then I take the integration. That will give me one value. Okay, so every value of this function of this convolution will give me the result of this particular integration. So you have to perform integration for each and every value of t. Okay, so this is what I mean. Okay, so suppose I have this function is f, okay, and this function is g. Okay, function f is a square function, function g is a triangular function. Okay, so what will happen is I'm taking here the horizontal axis is t, here also the horizontal axis is t, but here the horizontal axis is tau, because tau is the dummy variable, and then I use t minus tau. That means what I'm doing is I'm just, because here you can see here the slope is positive, so when you reverse it you will get a negative slope. Okay, you will get a graph that looks like this, and this, because I have put t minus tau, that means it will shift this, and now you change the value of t, so the shift will also go on changing. So for these different shifts we take the product of these two functions. Okay, the product of these two functions, wherever these functions have the same. In this case, it's got 0 values here, this also has got 0 values, here also 0 values, here also 0 values. So the product of these two functions will take maximum value whenever the overlap between these two functions is maximum. So in each and every case, we just find out what is the integral of the product of these two functions. So this is an animation which I have prepared using Scilab. So I'll just show it to you. Let me go one step at a time. Okay, let me pause it here. Okay, so you see what's happening here. This is the function. Okay, this is the function g. Okay, what we do is we reverse it. Here it was having a positive slope, here I make it as a negative slope. Why is this function g, why is it looking small here and why is it looking big here? Because the value here, the peak value here, it is 4.5 and here the peak value is 1. So that's the reason. Okay, so it is 4.5 and 1. So these two are actually scaled with respect to each other. Okay, so this is the function. Okay, this is the function g. So I have reversed it and I have shifted it by a certain amount. Now what I'll do is I find out the product of these two. Now what you see, wherever this function is non-zero, okay, this function g, wherever this function g is non-zero, function f is 0, and wherever this function f is non-zero, the function g is 0. So that means the product of these two functions for this shift, the product of these two functions will be 0 everywhere. So as a result, the integral of the product of these two will also be 0 here. Okay, now I shift this. Okay, when I shift this, again there is no overlap between them, so the product will still remain 0. Okay, so as a result, the value of the integral also will be 0. Now I shift this some more, again the same thing, no overlap between them, so the integral will be 0 again. So we have the 0 value here. Proceed some more and some more. Okay, this is the point where it just touches this. If you give some more shift, then it will have some overlap. So here at this point, this is the point. Here, this is the value of the convolution. Increase it some more, give it some more shift. Now what happens is, okay, there is some little overlap. You can see here a little bit of overlap here. So the function will be non-zero within this region. So if I take the integration of the product, I'll get some small value. Okay, so this is the small value you will get. Okay, because this is the shift at this value of t. This will be the small value that you will get. Give some more. Now the overlap has increased. Because the overlap has increased, so the value of the integral will also increase. So as a result, the convolution value will also increase. Shift it some more, the convolution value again it increases. This is the point where we have maximum overlap, right? You cannot get more overlap than this. So this is the point where we have maximum overlap. That means this point for this value of t. So this is where the convolution also becomes maximum. Now if you shift it some more, you see the overlap region, now it becomes again small. When the overlap becomes small, then the convolution also becomes smaller. Okay, after this point onwards, again it is going to become 0 because they don't have any region, any place where both of them are simultaneously non-zero. So after this, it is just going to be 0. So this is basically what happens in convolution. So we just look at what is the overlap. Okay, wherever the overlap is maximum, the convolution value is also going to be maximum, and then it's going to decrease. Okay, so this is what we mean by reversing one function and shifting the function. Okay, next is the first property of convolution is convolution is commutative. That it does not matter whether you take f star g or you take g star f. Okay, that means the dummy variable is tau here. It does not matter whether I reverse and shift g or I reverse and shift f. It does not matter. The convolution is going to be just the same. Again, this is a demonstration which I've used a Scilab to generate these animations. So this demonstration will actually show you the same thing. So here we have we'll try to obtain the convolution by shifting. This is g, the green curve. Okay, we will reverse this and shift the green curve, and here this is the blue curve, that is f. We'll reverse this and we will shift this. Okay, we'll change the shift and we'll find out what is the convolution. So here the first plot, it shows you both the functions. The second plot, it shows you whichever is the function that you are reversing and shifting. Okay, it will show you that function. The third plot, it will show you what is the product of these functions, and the last plot, it will show you what is the convolution. Okay, so let us consider this. Okay, Okay, so far so good. Okay, so I'm shifting this this function g, I'm shifting it slowly, right? So you can see here there is no overlap here, right? There is no overlap. Wherever g is non-zero, f is 0, and wherever f is non-zero, g is 0. So as a result, the product of this function will be 0. Okay, product of this function is 0 everywhere. So I bring this some more. Okay, now you can see here the product is increasing, right? Because there is some small overlap over here, so the product is gradually increasing. Shift it some more, the product is again increasing. Now what is convolution? The convolution is basically the integration of this function. Okay, the integration of this function will give me the convolution. Okay, till here the convolution is 0 everywhere. Now we have a little bit of overlap here. As a result, the product is non-zero here. You can see here there is a slight bump here. Increase this, you can see the convolution, it is increasing. Increase this some more, the overlap is increasing. As a result, the product will also increase, and hence the convolution will also increase. It will increase some more, the convolution is increasing. Okay, increase some more, and this is the point. This is the point where the overlap is maximum. Okay, this function and this function, they have maximum overlap when this g function is over here. This is where the product is also maximum, and as a result the convolution is also maximum. Beyond this, if we go, the product will decrease. The product is decreased. You see the area under this is decreasing. As a result, the convolution is also decreasing. Okay, so you have to look at what is the total area under this graph. This area under the graph is decreasing now, so the convolution is also decreasing. Okay, so now the area between in the graph is going to become 0. Now it becomes 0, no overlap between them, so the product becomes 0, and as a result, this is how the convolution is going to look like. Okay, so this is basically the convolution where I have reversed and shifted this g, function g, not the function f. The same thing we'll also be able to see. Okay, so you have seen how the convolution looks like. The same thing will happen if we, instead of taking g, instead of reversing and shifting g, if I reverse and shift f, then what will happen? The same thing is going to happen in this case also. Okay, so let me just, okay, now you see both of them. Here it is a function f which is being shifted. You can just keep an eye on these two subplots. You can see here the convolution is exactly the same in both the cases. Okay, so same convolution is, so that means the convolution is commutative. It does not matter which function you are reversing and shifting. Okay, so we go to the next property. So this is convolution which is commutative. Convolution is also associative. Okay, so it does not matter. Suppose I am having three functions f, g and h. It does not matter which convolution you perform first. So the convolution, the result is going to be just the same. And finally, convolution is distributive. Okay, so I'm having three functions. You are adding the last two functions g and h, and then the result you are taking convolution. This is the same as taking the convolution and then adding them together. This brings us to the Fourier convolution theorem, which is a extremely useful theorem, very straightforward. The Fourier convolution theorem, it basically says that if you take the convolution of two functions, okay, if I take the convolution of two functions f and g, and I find out the Fourier transform of this convolution, okay, the Fourier transform of the convolution of two functions, it is directly proportional to the product of the convolutions of the individual functions. So you find out the convolution of the first function, you find out the Fourier transform of the first function, then you find out the Fourier transform of the second function, multiply them together. Okay, whatever result you get, that is proportional to the Fourier transform of the convolution of the two functions. Okay, so this proof is very straightforward. So let's say we define this h as the convolution of two functions f and g. Okay, then the Fourier transform of h is, okay, we call it as capital H omega. It is nothing but Fourier transform of small h as a function of t, which is nothing but Fourier transform of f star g of t. So now we just use the definition of the Fourier transform. So 1 by root over twice pi integration minus infinity till plus infinity, integration with respect to dt, e to the power minus I omega t. Then this is the function that we are trying to integrate. Okay, Then we expand this, okay, using the definition of the convolution. F star g is nothing but minus infinity to plus infinity f tau g of t minus tau d tau. It does not matter whether you reverse and shift g or whether you reverse and shift f, okay, does not matter here because of the commutative property. So I have chosen to reverse and shift g here, okay. So this is what we get. Then h of omega will be equal to, okay, so what we do here is this e to the power minus I omega t, I'll take it over here, then f of tau I bring it over here, okay, and d of tau also I'm bringing here, because these are two independent integrations. This is integration with respect to t and this is integration with respect to tau, okay. So they are independent of each other, so that's why I'm able to separate them out, okay. So this is what we have, okay. So we call this equation number 1. So we'll just make a small substitution here. The substitution is this t minus tau, we call it as some other variable s, okay. So as a result dt will be same as ds. Then in equation number 1, okay, okay, here in this equation, because I'm making the substitution t minus tau, and when I take the differential, because t and tau they are independent of each other, so taking the differential of t, it is the same as taking the differential of s, because with respect to this integration tau is a constant, so that's why dt is equal to ds. So I make the substitution here. So g as a function of s, e to the power minus I omega, small t is equal to s plus tau, okay, we write down over here. Then we can make some manipulation here. This e to the power minus I omega tau, I take it outside and I combine this over here, okay. So e to the power minus I omega tau I bring in the first integral, and we immediately recognize this is nothing but the Fourier transform of the function f. Of course we have to multiply it with root over twice pi, and whatever is left, that is nothing but the Fourier transform of the function g. Of course here s is a dummy variable, so this is nothing but the expression for the Fourier transform of g. Of course we have to multiply this with root over twice pi, okay. So this is what we got so far. So root over twice pi, Fourier transform of f, root over twice pi, Fourier transform of g. So one of these root twice pi will get cancelled out, and eventually we will get the Fourier transform of the convolution of f and g is equal to root 2 pi times the Fourier transform of f times the Fourier transform of g. So that's the Fourier convolution theorem. So next we go to the properties of the Fourier transforms. The first property is differentiation. That is, suppose I have a function f of t and I want to find out the Fourier transform of the derivative of the function. Then all I have to do is find out the Fourier transform of the original function and just multiply it with I omega, okay. So differentiation is as simple as that, okay. So Fourier transform of the derivative is simply original Fourier transform, just multiply it with I omega, okay. So in general, Fourier transform of the nth derivative is simply I omega to the power n, the Fourier transform of the original function. Now this can be very easily proved, okay. So you just try taking the Fourier transform of the derivative, just expand this using the formula for Fourier transform. So instead of f, we'll have f prime, because we are trying to find out the Fourier transform of f prime, not f. So e to the power minus I omega t dt, okay. Small mistake here, there should be a single dt, which I will correct in the slides which I upload, okay. So this is, just read this as a single dt. Then what do we do? How do we solve this? We just use the integration by parts method. So integration by parts, so this is one function and this is, you take it as the other function. So all you have to do is take the functions as it is, so f and e to the power minus I omega t minus the integration of where the differentiation is reversed. So here you are trying to differentiate f of t, here we will differentiate e to the power minus I omega t. So differentiation of e to the power minus I omega t will give us minus I omega e to the power minus I omega t, and because the differentiation has shifted to this function, so therefore we have f of t. Now this is going to result to 0. Why will this become 0? Because we have defined like you can have the fact that we are able to find out the Fourier transform of f, that means the function f is absolutely integrable. That means it dies down at positive and negative infinity, and since we are taking the limits as minus infinity and plus infinity, at these two limits this function is going to die down, so as a result this will become 0. So then rest of it is very straightforward. This minus and this minus will get cancelled. So we have I omega which will come outside, 1 by root over twice pi minus infinity to plus infinity f of t e to the power minus I omega t dt, and this we immediately recognize, okay. This entire thing we immediately recognize as nothing but the Fourier transform of the original function. Okay, so this gives us the Fourier transform of the derivative is equal to I omega f of omega, and by using the principle of induction you can actually show that this result also holds good. Next, one more property is the integration. Okay, so if I have a function f of t and you are trying to integrate this function using a dummy variable tau, you are integrating from minus infinity till t, and then you take the Fourier transform of this, that will be nothing but the Fourier transform of the original function divided by I omega plus pi f of 0 delta omega, the Dirac delta function in the frequency domain, in the omega domain. To obtain this result, we find out the convolution first of we first find out the convolution of this function with the Heaviside step function. So f star h. Okay, so we reverse and shift the Heaviside step function. Okay, and we integrate from minus infinity till plus infinity. Now this is going to give us we only have to integrate from minus infinity till t. Okay, the reason for that is this h of t minus tau. Okay, h of t minus tau will look something like this. Okay, I just refer to my lectures on the Heaviside step function. Here the variable is not t, the variable is tau. Okay, so t is like a. Okay, the function whatever a is performing, so t is also doing the same thing. So I put minus t, that means you are reversing it, taking the reflection, okay, with respect to the vertical axis, and then you are taking a small shift here. So this is what we have. So this is how the Heaviside function step function will look like. Okay, so that's what we are multiplying. Okay, that's what we are multiplying here. Now because of this one, this what happens is this Heaviside step function, it takes the value 1 from minus infinity all the way from minus infinity till t, it takes the value 1. From t till plus infinity, it takes the value 0. So from minus infinity till t, this Heaviside step function will take the value 1. From t, imagine that I have split this integral from minus infinity to plus infinity. I write it as minus infinity till t, minus infinity till t, plus t till plus infinity. That integral from t till plus infinity, that will be anyway 0 because the Heaviside step function is 0, and what will be left behind is only this one. Okay, so this shows us that this quantity that we have, this integral that we have inside the bracket here, this integral is nothing but the convolution of the Fourier transform of the original function with the Heaviside step function. Okay, so if that is the case, then we are trying to find out the Fourier transform of this integral. So we can just replace this integral with the convolution of f and h. Now this is placed. So what are we trying to find out? We are trying to find out the Fourier transform of a convolution of two functions. Fourier transform of a convolution of two functions, we have already done the Fourier convolution theorem. So what the Fourier convolution theorem says is the Fourier transform of the convolution of two functions is root over twice pi times the Fourier transform of the first function times the Fourier transform of the second function. So by the Fourier convolution theorem, this will be root over twice pi times the Fourier transform of the first function, which is f of t, and the Fourier transform of the second function, which is h of t. Okay, so this is just the application of the Fourier convolution theorem. Okay, now this is very straightforward because we already know what is the Fourier transform of the Heaviside step function. We have already derived this some time ago. This is the Fourier transform of the Heaviside step function, and multiplied with the Fourier transform of the original function f of t. Okay, so this Fourier transform f of t, I'll just write it as capital F of omega. Okay, and we just take this root over twice pi inside, so this and this will get cancelled, and here we'll get a 2 pi. Okay, that's how you get this 2 pi here. So this will give us f of omega by I omega plus pi f omega delta omega, and this quantity will give us f of 0 and delta omega. Okay, how do you get this? This is by the shifting property of the Dirac delta function. You can refer to my lecture on the Dirac delta function. So over there I had one of the properties was the shifting property. I think let me just pull up the result here. Yes, this is a shifting property. Okay, so we use this same result, the same result I have used here. So that's how the product of these two will give us f at 0 delta omega. So this gives us this result that we are looking for, f omega by I omega plus pi f at 0 delta omega. So that's the integration property. Next we have 3 more properties. One is the scaling property, okay, and we have the translation property, and finally we have the exponential multiplication property. So with this we come to the end of this lecture on Fourier convolution. You can refer to both of these books, and I would suggest that you go through this article in Wolfram, okay, Math for Wolfram. There is a brilliant animation on convolution which is given there. This I think this is made using Mathematica. So you can, it's a good read. It's like a good summary of the concept of convolution. So this brings me to the end of this lesson. I will upload these slides as usual in Google Classroom, as also the problems that I had left to you as an assignment. Please feel free to get in touch with me in case you have any queries or any difficulties. Thank you.